In the previous chapter, we looked at probability distributions of discrete random variables, and we learned that the probability distribution provided the possible values of the variable along with their corresponding probabilities. And for discrete probability distributions, we knew that that distribution could be provided in the form of a table, in the form of a graph, or in the form of a mathematical formula. Well, now we're going to be looking at continuous probability distributions. And with continuous probability distributions, we have to have what is called the probability density function in order to obtain the probabilities of the continuous variable. So we have a definition here. A probability density function is an equation used to compute probabilities of continuous random variables. It must satisfy the following two properties. One, the total area under the graph of the equation over all possible values of the random variable must equal 1, and the height of the graph of the equation must be greater than or equal to 0 for all possible values of the random variable. So I want to begin by looking at the uniform probability distribution, and so we'll look at that through an example. So suppose that a utility worker is scheduled to install high-speed internet in your home between 10 a.m. and 11 a.m. Let X represent the time after 10 a.m. when the worker arrives. So this is a continuous random variable because the worker could show up at any sort of fraction of time after 10 a.m. Further, suppose that the worker could arrive exactly at 10 a.m., which means X equals 0, or exactly at 11 a.m., which means that X equals 60, with all intervals of equal time between X equals 0 and X equals 60 being equally likely. For example, the worker is just as likely to arrive between 10:05 and 10:06, that is between X equals 5 and X equals 6, as he or she is to arrive between 10:48 and 10:49, that is between X equals 48 and X equals 49. Then the random variable X follows a uniform probability distribution. It's called a uniform probability distribution because all of the intervals of equal time are equally likely. What is the probability that the utility worker will arrive between 10:20 and 10:30? If it's 10 a.m., there's a 30% probability the utility worker will arrive before what time? So now we have a uniform probability distribution. If I bring back in the previous sheet to describe this uniform probability distribution a little more clearly, the fact that it's uniform means that if this is the value of X, the time, and if here is 10 a.m., which is X equals 0, and if here is 11 a.m., which is X equals 60, so 10 a.m. X equals 0, 11 a.m. X equals 60, then if this is a uniform probability distribution, then the graph of the equation that we're going to use to figure out these probabilities is going to be a horizontal line so that it's uniform. Now, our requirement, again, was that two things. One, the total area underneath the graph has to equal 1, and the height of the graph has to always be above the x-axis. And so we meet both of those conditions, and so this graph ends over here, okay, at x equals 60. So because the total area beneath this line has to equal 1, then we can figure out what the equation of that line has to be. First of all, it's a horizontal line, and horizontal lines always have an equation of the form y equals b, where b is the y-intercept. Okay, so this would be the value of b. Okay, now we know that this gives us a shape of a rectangle, and since it's starting here at 0 and ending here at 60, the length of this rectangle is 60. And we know that the area of a rectangle is equal to length times width. So I can figure out the width or the height of this line because I know that the length 60 times the width w has to equal the area, which is 1. So the width of the rectangle has to equal 1/60th. In other words, that has to be at a height of 1/60th, which means it's crossing at 1/60th up the y-axis. So the equation of this horizontal line has to be y equals 1/60th. Now, so we know the uniform probability distribution. This is our probability density function, and we can use that to answer the questions. Now, again, we want to know what is the probability the utility worker will arrive between 10:20 and 10:30. Well, 10:20 means that would be 20 minutes after 10, and 10:30 means that would be 30 minutes after 10. So here x equals 20 and here x equals 30. So again, if I redraw my uniform probability distribution, so here is x equals 0, here is x equals 60. Again, this is representing 10 a.m., this is representing 11 a.m., and we know that this is y equals 1/60th. That's the equation of that horizontal line. So x equals 20 would be around right here, and x equals 30 would be around right here. So this area beneath our probability density function will equal that probability. So if I can find the area between x equals 20 and x equals 30 that's below our probability density function y equals 1/60th, that will be the probability. So in this particular case, again, we have the shape of a rectangle. And since this shaded rectangle starts at 20 and ends at 30, that means the length there is 10. And we know the width or the height of that rectangle is 1/60th. So that area right there is going to equal the length 10 times the width 1/60th, and 10 times 1/60th is 1/6. So the probability that the utility worker will arrive between 10:20 and 10:30 is 1/6. Now, part B. It's 10 a.m., and so there's a 30% probability that the utility worker will arrive before what time? So this problem's kind of going backwards. We have the probability, and we want to figure out the time that the utility worker will arrive before, if that is the probability. So again, if I draw my probability density function, again, this is the line y equals 1/60th. Here is 11 a.m., which is x equals 60. Here's 10 a.m., which is x equals 0. So again, this is representing 10 a.m., this is representing 11 a.m. Okay? So we have some time here so that this area is going to be 0.20 for the probability. Okay, so again, these areas are representing the probabilities. So can we figure out what x has to be? Well, if this value is x, then that means the length from 0 to x is x. We know the width is 1/60th. So 1/60th times x has to equal the 30%. I wrote 20% there earlier, but it should be 30%. So that has to equal 0.30. Okay? So we can solve for x by multiplying both sides by 60. So if I take 0.30 times 60, that is 18. So this would be where x equals 18. So there's a 30% chance that the utility worker will show up within 18 minutes or before 18 minutes after 10 o'clock. So the question was before what time? Well, 18 minutes after 10 o'clock would be 10:18 a.m. So again, there is a 30% probability that the worker will show up before 10:18 a.m.